There's a galaxy whose bright main body is measured at around 114 kiloparsecs across roughly 370,000 light-years, meaning you could line up almost 4 Milky Ways end-to-end inside it. Astronomers pinned it down while studying the giant galaxy cluster Abell 2029 and mapping the massive central system at its core. That galaxy is IC1101. Now hit your intuition with the raw numbers, because they don't feel real at first. This galaxy is roughly 354 megaparsecs away, around 1.15 billion light-years. That means the light you receive today left when Earth was a different place, and it travelled while the universe expanded the whole time. The recession velocity is around 22,419 kilometers per second, so you're not seeing it as it is now in some absolute sense. You're seeing it across a long stretch of cosmic time and expansion. That matters because when you talk about size, brightness, and structure, you're measuring something far away with faint light, and small errors can become big disagreements. People call this galaxy one of the biggest stellar aggregates we know, and that phrase sounds clear. But it hides a problem. In a cluster, the word galaxy gets messy at the edges. Stars can exist in a smooth outer envelope around the central galaxy, and also in intracluster light, stars that are not bound to any one galaxy anymore. You can detect that starlight, but deciding what counts as the galaxy versus the cluster's shared light is not always clean. Nature doesn't put a border around it. Astronomers have to define boundaries using specific measurement rules, and those rules change the result. So the first major stake is this. This galaxy is not just a big object to rank on a list. It's a test case for how growth works at the extreme end. The main idea in modern cosmology is hierarchical growth. Small things are formed first, then merge and accrete over time, building bigger structures. For normal galaxies, that story works pretty well. But when you see something this large at a cluster center, you're forced to ask if the same growth picture holds up, or if you need extra processes, like repeated mergers, tidal stripping, and the blending of galaxy light with cluster light to explain what you're measuring. And that's why this is a stress test, because every part of the standard story gets pushed hard here. If this galaxy formed mainly by mergers, it should show signs of heavy merger history in its structure, its core, and its outer light profile. If it formed mainly by grabbing strip stars from other galaxies in the cluster, then the boundary between galaxy and cluster becomes part of the science, not a detail to ignore. Either way, what you conclude depends on how you define what counts as belonging to the galaxy. Now here's the promise of the episode, and it's going to keep getting more intense. You're going to watch the idea of galaxy size split into different definitions, and none of them will make this galaxy feel normal. Size can mean whether light drops below a chosen brightness threshold. Size can mean the radius that contains half the total light. Size can mean the region where stars are still gravitationally bound mainly to the galaxy, instead of the cluster. These are not small technical choices, because changing the definition can change the size by huge amounts, and it can change whether something qualifies as the largest at all. So the key point right now is simple. Even before we argue about the exact edge, this galaxy is already extreme by any reasonable metric. But the deeper point is more important. The word galaxy is not a perfect label in rich cluster centers, and this object makes that impossible to ignore. Now, lock onto the next tension step. If the environment is doing this much work, if the cluster is affecting the outer stars, the mergers, the stripping, then you can't understand this galaxy without understanding the cluster it lives in. So what kind of cluster can support something this huge? And what does its hot gas and gravity do to the story? How can a galaxy be the biggest if the real power is the thing it lives inside? Abell 2029 is the reason this story even exists. You don't get IC 1101 without a massive cluster that can hold onto matter, pull galaxies inward, and keep the centre busy for billions of years. A cluster like this is not just a group of galaxies, it's a huge gravitational structure dominated by dark matter, filled with hot gas, and packed with galaxies moving at high speeds. That deep gravity well is the engine. It sets the traffic patterns, and it sets the merger rates, and it sets what kind of central galaxy can even form. Here's the part most people miss. The cluster is not mostly stars. The big visible galaxies are the easy part to notice, but a large fraction of the normal matter in a rich cluster is actually gas, so hot it glows in X-rays. That's why Abell 2029 is described as X-ray bright. You're seeing the intracluster medium, the ICM, a thin plasma that fills the space between galaxies. Thin matters. It's far more rarefied than air, but it's spread across an enormous volume, so in total it carries a huge amount of mass and energy. That hot gas is not just background, it shapes what galaxies can do. When a smaller galaxy falls into the core, the ICM can strip its gas away through ram pressure. Basically, the galaxy is moving through a hot medium and its own gas gets pushed out. Without gas, star formation shuts down. So the cluster environment tends to make galaxies stop forming new stars over time. That means growth at the center becomes less about making new stars, and more about adding existing stars from other galaxies through mergers and stripping. Now lock onto the temperature profile, because it tells you the cluster is not uniform. Chandra observations show the gas is hotter farther out, around about 9 keV, and cooler in the inner core, around about 3 keV. keV sounds like a weird unit. But in X-ray astronomy, it's a standard way to talk about temperature for gas that's tens of millions of degrees. So when that number drops toward the center, that's not tiny detail. It's telling you the core gas is in a different physical state, cooling more efficiently, and interacting with the central region in a special way. This also tells you something else. The gas is tracing the gravity. Hotter gas generally means the particles are moving faster, and that usually connects to how deep the gravitational potential is. By mapping gas temperature and density in X-rays, astronomers can estimate how much total mass sits inside different radii. That includes dark matter, because dark matter dominates the gravity. So the X-ray brightness and temperature structure are not just nice observations, they are a way to weigh the cluster and understand how strong the environment is around this galaxy. Now, why does it matter that Abell 2029 is often called relaxed? Because relaxed means, compared to a cluster in the middle of a major crash, this one looks smooth and settled. The X-ray emission is more symmetric, the center is well defined, and the gas is closer to a stable balance with gravity. That matters because it lets astronomers do cleaner physics. If the gas is roughly in hydrostatic equilibrium, meaning pressure support balances gravity, then the X-ray profiles can be used to estimate the mass profile with fewer unknowns. And if you can estimate mass better, you can reconstruct merger history better, and you can judge how much the cluster should be affecting the galaxy at the center. And this is why a relaxed cluster is a valuable laboratory. You can compare X-ray mass estimates, galaxy distributions, and simulations with fewer excuses. When the system is chaotic, it's hard to tell if your model is wrong or the cluster is just mid-crash. Here, the baseline is cleaner, so any weirdness near the center is harder to dismiss. But here's the tension. Relaxed does not mean inactive. Even in a relaxed cluster, the core keeps evolving on long timescales. Galaxies keep orbiting through the center. Their orbits can shrink over time due to dynamical friction. Basically, they lose orbital energy to the surrounding mass distribution, so they drift inward. Close passes and minor mergers keep happening. Tidal forces pull at the outer parts of the galaxies because the cluster's gravity can overpower the galaxy's self-gravity in the outskirts, so the environment is not empty space around a galaxy. This galaxy sits inside a hot atmosphere and a deep gravitational field that keep recycling material. Over time, you build a very extended low-surface brightness component around the center. From a distance, that light can look like one enormous halo. But physically, some of it can be stars still orbiting mainly the galaxy, and some of it can be stars orbiting mainly the cluster. And this is the key twist that keeps coming back. In rich clusters, the thing you see around the brightest cluster galaxy can be two things at once. Part of it can be a true galaxy envelope, part of it can be intracluster light, stars that are not bound to any single galaxy anymore. Photometrically, just from brightness, those components can blend together. Nature does not label the boundary. If you draw the edge based only on how faint the light gets, you may be mixing two different physical populations and calling it one object. So when you hear this galaxy is unbelievably large, you should immediately add a second sentence. Large by which definition, and large compared to what physical boundary? Because in Abell 2029, the center is where boundaries get hardest to define, and where the difference between galaxy and cluster becomes a real measurement problem. And now the pressure rises, because if the environment can blur the edge this much, then size is not a single number. So how do astronomers actually measure how big something is? And why can the same object be quoted with wildly different diameters depending on the method? How do you measure the size of something when the edge is so faint you can't even tell where it stops? IC 1101 is where the word size stops being a simple number, because astronomers don't measure a galaxy's edge like a wall. They measure light, and light fades gradually. So how big depends on the rule you choose, and that rule can change the answer by hundreds of thousands of light years. Start with the most common trap, isophotal diameter. That's a technical way of saying pick a brightness level, real, then draw the outline where the galaxy's surface brightness falls to that level. Surface brightness means how much light you get from each patch of sky, not the total light added up. One classic threshold is called D25. It uses the B band, blue light, and it sets the boundary where the surface brightness reaches about 25 magnitudes per square arc second. In normal language, it's the point where the galaxy becomes faint enough that surveys historically felt confident saying, past this, we stop. But here's the punch. That cutoff is a human choice. Nature did not pick 25. D25 became popular because older surveys could reach it reliably, and because it worked nicely for many normal galaxies. But for a giant central galaxy with a huge faint envelope, the choice is not neutral. Go a little deeper, and the edge can jump outward fast, and the background is never perfectly clean. Telescopes have scattered light. Detectors have noise. Foreground stars need to be masked. Faint gradients across the image need to be corrected. So if you choose a brighter cutoff, you stop sooner and the galaxy looks smaller. If you push to a fainter cutoff, you include more of the outer envelope and the galaxy looks larger. With the galaxy, the outer light falls off so slowly that small changes in cutoff can create huge changes in reported diameter. Now listen to the range that causes arguments. The isophotal diameter people cite for this galaxy is often quoted around roughly 123 to 170 kiloparsecs, about 400,000 to 550,000 light-years, depending on the band and method. That difference is not a rounding error. That difference is the definition fighting the background, and the background fighting your abilities to see faint light accurately. So why does the band matter? Why does blue light give one answer and infrared can give another? Because different wavelengths highlight different parts of the galaxy. Blue light is more sensitive to young stars and recent star formation, and it is strongly affected by dust. Dust absorbs and scatters blue light more easily, so blue can hide some starlight and also overemphasize small bright patches. Infrared, like the K-band, is less sensitive to dust, and it is dominated more by older stars. Older stars tend to trace the bulk of the stellar mass more reliably, so K-band imaging can reveal a smoother and often more extended structure, closer to where most of the mass really is. And here's the next tension jump. If infrared lets you track faint light farther out, are you measuring the galaxy, or are you starting to measure stars that belong to the cluster environment? Photometry alone can't fully answer that, because faint cluster light can blend with the galaxy's outer envelope. At this distance, surface brightness measurements are already hard, and the fainter you go, the more your result depends on background control. Now switch definitions, because this is where the leaderboard can flip. Effective radius, also called the half-light radius, doesn't ask where is the edge. It asks how far out do you go before you enclose half the total light. That sounds more physical, but the catch is brutal. To get the half-light radius, you need the total light. To get the total light, you need to decide how far the light extends, how to subtract the background, and how to model the faint outskirts you cannot measure perfectly at extremely low brightness. Models matter a lot here. Big ellipticals are often fit with a Sayersic profile, a smooth curve that describes how brightness drops with radius. A tiny change in the outer slope changes how much total light you think exists at large radii. If the profile declines slowly, the integrated light keeps growing, so half the total light can sit very far out. That means a galaxy can look not that wide by a bright isophotal cutoff, but still have a very large half-light radius, because so much light is spread into the outskirts. Now add the hardest practical issue, sky subtraction. When you measure extremely faint outer light, the dominant signal is often the background, not the galaxy. If your background estimate is off by a tiny amount, you can accidentally create a fake extended halo, or erase a real one. That's why different teams can publish different sizes while working honestly. They can use different instruments, different filters, different ways to correct scattered light, different strategies to mask sources, and different choices for how to fit the outer profile. So when someone says largest galaxy, your first response should be largest by which definition? Isophotal diameter at which surface brightness threshold? In B-band or in K-band? Half-light radius based on which profile fit? Total stellar mass based on which calibration? Or the radius where stars are still mostly bound to the galaxy's own gravity, rather than dominated by the cluster? Which is not a photometry question at all. That's a motion question. And here's the stakes escalation. The moment you change the definition, you change the ranking. One study can put this galaxy at the top using one cutoff. Another can shrink the quoted size using stricter background control or a different band, and both can be scientifically valid. So largest galaxy is not a trophy. It's a measurement argument, and the argument is the science. So the next question is unavoidable. If brightness alone can mix galaxy halo with cluster light, how do you separate them using physics instead of a threshold? You don't just measure light, you measure how the stars move.
Why does this galaxy look like it has two bodies, a normal-looking center, and then a huge faint extension that just refuses to end?
IC1101 is not a weird exception. It is an extreme example of a known blueprint. In rich clusters, the central brightest galaxy often belongs to a class called a CD galaxy. CD basically means a very large central galaxy with an extra extended envelope that goes way beyond what you'd expect from a normal elliptical. And that envelope is the key because it's not just decoration. It's evidence that the cluster center has been active for a long time. Here's the straight version. A CD galaxy is oversized because it grows in the one place where the cluster keeps delivering material. The cluster's gravity funnels matter toward the center, not in a smooth flow like water, but through orbital decay, mergers, and stripping. Over billions of years, the central galaxy absorbs other galaxies and also picks up stars that get torn out during close interactions. The end result is a central object that can look like a normal giant elliptical in the inner region, but has a much larger diffuse component outside it. That's why people say a CD galaxy is like a long-term merger record. Not in a poetic way, in a literal measurable way. The outer structure keeps track of how much accretion happened, how often mergers occurred, and how much stripping added stars to the outskirts instead of leaving them in separate galaxies. So what do astronomers actually see when they say this is a CD? The observational signature is usually a smooth light distribution, a huge halo, and a very central position in the cluster. Smooth matters because repeated mergers and stripping tend to erase sharp features over time. A huge halo matters because it signals a lot of starlight at large radii, often at very low surface brightness. And the central position matters because it's not random. The cluster's center is where the gravitational potential is deepest, so it's where you expect the most massive central galaxy to sit and to keep growing. Now, here comes a term you've probably heard: galactic cannibalism. It sounds dramatic, but it's a real physical process and it can be quantified. In a cluster, galaxies orbit through a background of dark matter, gas, and other galaxies. When a galaxy moves through that background, it creates a gravitational wake. Basically, it perturbs the distribution behind it. That wake pulls back on the galaxy and steals orbital energy. That process is called dynamical friction. Over time, dynamical friction causes massive galaxies to lose energy and sink toward the cluster center. Once they get close enough, mergers become more likely. The central galaxy grows. But the growth is not always eat the whole thing cleanly. Often the outer parts of the incoming galaxy get stripped first, and those stripped stars spread into the central region as diffuse light. So you get two growth channels happening at once: direct merging into the core and gradual build-up of an extended envelope from stripped stars. That is why the outer halo can become enormous, even when the inner galaxy looks like a standard elliptical. And this is why brightest cluster galaxies break tidy categories. If you try to classify galaxies by simple shapes, spiral, lenticular, elliptical, you run into trouble here. A BCG can look like a normal elliptical or lenticular-like core in the center, but it sits inside a much larger diffuse component that doesn't behave like a normal galaxy disk or a standard elliptical profile. It's more like an inner galaxy embedded inside a broader light distribution that connects to the cluster environment. That's why, what type of galaxy is it? becomes a harder question than most people expect. The answer can be, there's a core that looks like one thing, and an extended envelope that is a different component with a different origin.
Now push the stakes again, because this connects directly back to the largest galaxy argument.
If the extended envelope is built partly from stripped stars, some of those stars might not be tightly bound to the galaxy at all. They might be moving mainly in the cluster's gravitational field. Photometrically, the light blends structurally. It looks continuous, but physically it might be a mix of galaxy halo and intracluster light. So when someone quotes a size, you have to ask, are they measuring the inner galaxy, or the galaxy plus its envelope, or the envelope plus part of the cluster light? Each choice can be defended, and each choice changes the result. And now the key hook that people get wrong all the time, this is not a big Milky Way. The Milky Way is a star-forming spiral with a disk, gas, and ongoing star birth. This galaxy is the outcome of a very different growth path, dominated by the repeated mergers, stripping, and long-term accumulation at a cluster center. It's what happens when gravity has a dense environment to work with for billions of years, and it keeps adding stars without needing to form many new ones. So here's the next tension question. If the extended envelope is one of the defining features, then the next thing that should break your brain is the faintest part, the outer light that is so weak it can be confused with background errors. How do you even know the halo's real? And how far does it actually go? How can you claim the outer edge of this galaxy when the main thing you're fighting is your own telescope? XC1101 is famous for its extreme size claims, but the part that really causes the debate is not the bright center, it's the faint halo. The outer light is so weak that it lives in the danger zone, where a tiny mistake in background measurement can create a discovery that isn't real, or erase a real structure like it never existed. This is the diffuse light problem. At large radii, surface brightness drops fast, and then keeps dropping until it's barely above the sky background. And the sky background is not a perfect flat sheet. It has gradients, it changes with time, it includes scattered light from bright stars and faint unresolved sources, and instrument effects. If your background subtraction is off by a small amount, that error gets integrated over a huge area, and it can look like a smooth halo extending way farther than it truly does. And this galaxy is exactly the kind of object where that can happen, because the outer profile is smooth and extended. There aren't clear, sharp edges. There's no obvious stop point. So the measurement becomes, how deep can you go before your uncertainty becomes bigger than the signal? Now let's talk about the jaw-drop claim that gets repeated a lot. Reports of a very extended low-intensity halo reaching out to hundreds of kiloparsecs. Hundreds. That scale is so large that it starts sounding like you're measuring a significant part of the cluster core, not just a single galaxy. But here's the problem. At that level, the result is extremely sensitive to assumptions. First, distance assumptions matter. If you change the distance estimate, the conversion from angular size on the sky to physical size changes. That can inflate or shrink the halo size directly. And because different papers can adopt slightly different cosmological parameters or different redshift-based distances, you can end up with different physical radii for the same observed angular extent. Second, band and data processing choices matter. If one team measures in one filter and another team uses a different filter, they are not tracing the same stellar population the same way. If one team uses aggressive sky subtraction, the halo can shrink. If another team leaves a small residual gradient, the halo can grow. Both teams can be careful and still get different answers because the signal's near the limit. Now the key observational reality at these surface brightness levels. You need meticulous calibration. This includes controlling scattered light inside the instrument, correcting flat field errors, masking stars and galaxies properly, and verifying that what you call halo is not actually light from the telescope optics spreading out bright sources into a faint glow. Scattered light is sneaky because it creates a smooth extended pattern, exactly the shape you might think a real halo should have. So you have to measure the instrument response carefully, or you can detect a huge envelope that is partly an artifact. This is why deep imaging work on faint halos often spends as much effort on systematics as on the actual signal. You don't just take a long exposure and call it done. You test background stability, you compare different nights, you check against different instruments, you model the point spread function, basically how a point of light gets smeared by optics, because the wings of that smear can mimic extended emission. If you skip those steps, the halo you publish can be your equipment talking back to you. Now here's the important point. Even if you downsize the extreme halo claims, this galaxy is still huge. Even conservative isophotal measurements using standard brightness thresholds already put it among the largest known by optical and infrared size metrics. So the debate about the farthest faint light is not about whether it's big. It's about how big and what that outer light physically represents. And that leads straight to the bigger stakes, because the halo is the zone where the word galaxy starts dissolving into cluster. At smaller scales, you can usually pretend a galaxy is a separate object. It has stars that orbit mainly in its own gravitational field. It has a profile that drops off and becomes negligible. But in a rich cluster center, the outer stars may be influenced more by the cluster's gravity than the galaxy's gravity. Some of that light may be from stars stripped off other galaxies, now floating through the cluster core. And photometrically, those stars can blend smoothly with the galaxy's envelope. So when you ask how far does the halo go, you're also asking which stars count as belonging to the galaxy. And that is not a word game. It's a physics question about orbits and binding. If the outer stars are moving mainly in the cluster potential, then calling them part of the galaxy is an approximation. If they are still mostly bound to the galaxy, then the galaxy is truly that extended. Without motion data, deep imaging alone can't fully decide. So here's the tension step that pushes this into the next section. If the outer light can be real starlight, but not bound to any one galaxy, then what are you actually seeing around the center of a cluster? And how do astronomers separate galaxy halo from intracluster light without guessing? What if a large part of the light you're calling this galaxy is not actually part of any galaxy at all? IC 1101 sits in the exact kind of environment where intracluster light, ICL, becomes unavoidable. ICL is real starlight from real stars. But those stars are not bound to any single galaxy anymore. They are the leftovers of past interactions, galaxies passing close, getting tidally stripped, merging, and losing stars into the cluster's gravitational field. Those stars keep orbiting the cluster as a whole. They don't disappear, they just stop belonging to one clean object. This is where people get confused, because ICL does not look like a bunch of separate streams from far away. Over long times, and after many interactions, the stripped material can become smooth and spread out. It forms a very faint glow that sits between galaxies, and especially around the cluster center. And that's the problem. The brightest cluster galaxy already has a faint extended envelope. The ICL also becomes strongest near the center. So when you take a deep image, the two can blend into one continuous-looking light profile. Photometry alone, meaning just measuring brightness versus radius, can't always separate them. You can draw an isophote, you can pick a surface brightness cutoff, you can fit a model, but you're still making choices. And near the center of a rich cluster, those choices can quietly decide whether you're measuring the galaxy or the cluster light.
So what's the key trick that breaks the tie?
Motion, kinematics, meaning how stars and tracers move or can separate what photometry blends. If stars are mainly bound to this galaxy, their velocity distribution should reflect the galaxy's gravitational potential. If stars are mainly part of the cluster, their velocities should look more like the cluster's broader potential, usually higher dispersions, and a different radial behavior. In simple terms, you don't just ask, where is the light? You ask, what is the light doing? Now, measuring kinematics in extremely faint outer regions is hard. You're dealing with low signal. You often use bright tracers like planetary nebulae, globular clusters, or integrated light spectroscopy in deep exposures. But when you can do it, it's powerful because it turns edge debates into physical membership tests. And this is why ICL is scientifically explosive. It's not just a side effect, it's a fossil record. The amount of ICL, spatial distribution, color and metallicity trends, and its kinematics all encode the history of the whole cluster. More stripping and merging over time, more ICL, more late-time accretion, different gradients, different orbital histories, different shapes. You can use the ICL to infer how quickly the cluster assembled and how violently the cluster core has been processed. And here comes the shatters what we assumed moment, because it targets the headline claim directly. If a big fraction of the faint light near this galaxy is actually DEL, then the phrase largest galaxy becomes conditional. Conditional on what you include. If you include the full extended envelope all the way out, you may be counting stars that are orbiting the cluster, not the galaxy. If you exclude too much, you may throw away a real bound halo. So the ranking depends on a definition, and the definition is tied to physics, not popularity. This is not pedantry. This decides what you think you're measuring. And the hard data angle here is that modern studies don't just eyeball this. They measure ICL profiles out to large radii on purpose and compare them to cluster mass profiles. The logic is simple. The cluster's dark matter profile sets the gravitational structure. The hot gas profile in X-rays traces the potential too. If the ICL is really a cluster component, its distribution should connect to those mass tracers, so people measure the starlight at very low surface brightness and compare it to lensing maps, X-ray mass estimates, and dynamical models. The goal is to connect the visible diffuse light to the invisible mass, so you can see how stars and dark matter are arranged together in the cluster core. And now the tension tightens again, because once you admit that part of the galaxy halo might be cluster light, the next question hits harder. If this galaxy has grown through repeated mergers, then its center should show damage, not just growth. Something should be different about the core itself, not the outskirts. So what happens when you look at the very middle and you find a core that looks like it's missing stars? How can the center of this galaxy look emptier than it should, when gravity should be piling stars inward? IC1101 has one of the most extreme core claims in the nearby universe of giant cluster galaxies, an extremely large depleted core. The reported break radius is around 4.2 kiloparsecs. Stop and translate that. Typical depleted cores in big ellipticals are on the scale of tens to hundreds of parsecs. This is thousands of parsecs. That's not a bit bigger, that's a different category. So what does depleted core mean in normal language? It means the very centre has fewer stars than you would expect if you took the outer light profile and smoothly extended it inward. In other words, if you fit the galaxy's brightness profile outside the core and ask, what should the centre look like if nothing special happened? You predict a steeper rise in brightness, but the real data shows a flattening, a deficit. It's like the centre was partially emptied out compared to the simple expectation. That sounds weird until you remember. Stars are test particles. They respond to gravity. If something in the centre changes violently enough, stars can be pushed outward or ejected. And in giant galaxies, there is one mechanism that has strong support and shows up again and again in both theory and observation. Supermassive black hole mergers. Here's the best supported picture. When galaxies merge, their central supermassive black holes don't instantly combine. First, the two black holes sink toward the common centre through interactions with stars and gas. Eventually they form a bound binary, two black holes orbiting each other. Now you have a very efficient way to remove stars from the centre. A star that passes near this binary can get a gravitational slingshot. The binary transfers orbital energy to the star. The star gets kicked outward, sometimes even out of the galaxy entirely. The binary tightens. Repeat this over huge numbers of interactions, and you scour the central region. You remove stars from the core, and you create a depleted core. This is not a minor effect. If you have one major merger with two big black holes, you can carve out a noticeable deficit. If you have multiple major mergers over time, you can carve out a much larger one. That's why the size of the depleted core is treated like a record of how much violent merging the central region has experienced. So now the stakes jump. A core with a break radius reported around 4.2 kiloparsecs is not easy to explain with one merger. It strongly suggests a history of multiple major mergers, not just small satellites being absorbed, but big galaxies coming in with their own central black holes. That means this galaxy's present-day structure is not one story. It's the sum of many galaxies that used to exist as separate systems, and then were destroyed and combined in the cluster center. That's the clean version of the graveyard point. It's not a metaphor you need to accept emotionally. It's a physical inference. To get a core that depleted, you need repeated episodes of black hole pairing and stellar ejection. Each episode requires a substantial merger history, so the core is a scar. Evidence of a long sequence of big collisions.
Now, how do astronomers actually quantify a depleted core instead of just claiming it?
They fit the surface brightness profile with a model designed for this situation. One common approach is the core-Cercic profile. Outside the core, the light follows a Cercic-like curve, smooth decline with radius. Inside the core, the profile transitions to a shallower slope. The break radius is where that transition happens. From the fit, you can estimate the amount of light missing compared to what the outer profile would predict. That missing light is linked to the amount of stellar mass removed, and that can be connected to the black hole mass and the merger history through models. They also look at the inner slope, how flat the brightness gets near the center, and how sharp the transition is. Different shapes can indicate different dynamical histories, like how many mergers happened and how the black hole binary hardened over time. Now here's the tension you should feel building. If the core is this extreme, then the central black hole history must also be extreme. You can't talk about a giant depleted core without talking about the engine that can carve it. Which raises the next question. How big might the central supermassive black hole be? And how do you even estimate that when you can't directly weigh it easily at this distance? How big does a black hole have to be to reshape the center of this galaxy on kiloparsec scales. IC1101 sits in the exact place where the biggest black hole claims keep showing up. Brightest cluster galaxies. That's not hype, it's the basic logic of growth. The cluster center gets more mergers. More mergers means more chances to bring in another supermassive black hole. Over time, those black holes can merge and grow. Also, these central galaxies have huge stellar masses and huge dark matter environments, so the conditions for building extreme black holes are there more often than in normal galaxies. But now comes the hard part. How do you actually estimate the mass of a supermassive black hole in a galaxy this far away? Especially when you can't resolve the very tiny region where the black hole's gravity dominates. Astronomers use handles. These are indirect measurements that correlate with black hole mass. They're useful, but none of them are perfect. One big handle is stellar velocity dispersion. That's basically how fast stars move around in the central region, not in ordered rotation, but in random directions. In many galaxies, higher dispersion means a deeper central gravitational potential, which tends to correlate with a more massive black hole. This is the basis of the famous scaling relation between black hole mass and dispersion. It's powerful because you can measure dispersion from spectra even when you can't see individual stars. Another handle is the central light profile, especially whether the galaxy has a depleted core. Core size and missing light can be linked to black hole merger history. If a binary black hole ejects stars and scours the center, a larger depleted core can point to more massive black holes or multiple major mergers, or both. This is not as clean as dispersion because it depends on modeling and assumptions, but it's still informative. A third handle is scaling relations with the bulge mass or luminosity. In many galaxies, the black hole mass correlates with the mass of the central spheroid. For giant cluster galaxies, people often use these relations because they can estimate stellar mass from photometry and population models. Again, useful but with big uncertainties, especially when the outer envelope and intracluster light make total galaxy mass harder to define. So what's the honest message? The most extreme black hole mass numbers you see for giant central galaxies often come with large uncertainties. The data is hard, the system is complex. The relations were calibrated mostly on nearer galaxies with better resolved centers, and then extended to more extreme objects. That doesn't make the estimates worthless, but it means you should treat the biggest numbers as upper-end candidates, not a single clean winner with a perfect measurement. And this galaxy is a perfect example of why. The environment blurs the outer structure. The center has a huge depleted core. The velocity, dispersion, and light profile can be measured, but interpreting them depends on which components you include and what model you trust. Now connect this back to the depleted core, because this is the strongest tension link. If the core really is carved by repeated binary black hole scouring, then that's indirect evidence of repeated supermassive black hole pairings at the center. You don't get multiple pairings without multiple significant mergers, and you don't get a huge core deficit without strong gravitational interactions that can eject large numbers of stars. So even if you don't claim one exact black hole mass, you can still say something solid. This system likely hosted major black hole merger activity over time. And that pushes the shatter moment, because at this scale, black holes stop being just objects sitting in a galaxy. They become part of the galaxy's architecture. They influence the central density profile. They help decide how the inner region looks. They can affect how stars are distributed. In other words, the black hole is not just a point mass you add at the end of the story. It's one of the processes that shapes the final structure you measure. Now here's the pressure increase for the next section. If the centre and the envelope were built over different times, by different processes, then the stars themselves should carry evidence of that, not in a vague way, in measurable fingerprints, ages, metallicities, gradients. So what does the light from the stars actually say about when this galaxy grew, and how it assembled? How can you tell when this galaxy grew if all you see is a smooth glow? IC1101 is too far and too complex for simple guesses, so astronomers go to the most direct evidence they can get from starlight spectra. A spectrum is basically light split into its colours very precisely. Inside that light are absorption lines, tiny dips at specific wavelengths made by elements like iron, magnesium, calcium. Those features let you estimate two key things: how old the stars are on average, and how metal-rich they are. In astronomy, metals means anything heavier than helium. More metals usually means the gas was processed through more generations of stars before forming the stars you see now. So what do you typically find in brightest cluster galaxies? You usually find old stellar populations, meaning most of the stars formed a long time ago. That matches the idea that the dense core formed early, when the universe was forming stars more actively. But you also often find gradients, meaning the stellar population changes with radius. The centre can be more metal-rich and sometimes slightly younger or more complex, while the outer regions tend to be more metal-poor on average. Those gradients are important, because they hint the galaxy was assembled in layers, not formed in one clean event. Now, what pattern do you expect if a giant central galaxy was built mainly by mergers? You expect a dense inner component that formed early and got enriched quickly, so it ends up metal-rich. Then you expect an outer envelope that was added later by accretion, meaning it was built from many other galaxies that got merged in or stripped apart. Those incoming galaxies, especially smaller ones, tend to have lower metallicity because they had less efficient chemical enrichment. So when their stars get added to the outskirts, the outer parts become more metal-poor on average. That's the key idea. Inner region formed early and fast, outer region built later, and messy from many sources. And this is why people care about chemical fingerprints so much. Metals are timestamps, not perfect timestamps, but strong clues. If the stars are very old and very metal-rich in the centre, that points to early rapid star formation when gas was dense and formation was efficient. If the outskirts are older but more metal-poor, and maybe show a mix, that points to a long history of accreting and stripping other galaxies, sometimes over billions of years. So with stellar populations, you can ask a timeline question in a measurable way. Did most of the mass assemble early or with little change after, meaning the galaxy mainly finished long ago? Or did the galaxy keep building its outer envelope late, meaning the core is old but the structure kept growing by adding stars that formed elsewhere? The outer population gradients are one of the cleanest ways to test that. Now bring in the cluster environment effect, because it changes the rules. In dense cluster environments, quenching is common. Quenching means star formation shuts down. The reasons include gas stripping by the hot intracluster medium, heating and feedback, harassment, and the simple fact that cold gas is harder to keep in a fast-moving dense environment. Once galaxies in the cluster core lose their gas, they stop making many new stars. That means growth in the core becomes dominated by mergers and accretion of existing stars, not by forming lots of new ones. So the growth mode shifts. Instead of build mass by making stars, it becomes build mass by adding stars that already exist. That makes stellar population gradients even more important. They preserve evidence of where those stars came from. The outer envelope can be a mix of many donor populations, each with its own chemical history. Now the stakes escalate again, because this connects directly to the largest galaxy problem. If the outer halo is mostly accreted, then the extreme size is not telling you one galaxy formed insanely large in place. It's telling you the cluster center has been collecting stars from many systems and building an extended structure over time. That means the outer light is literally cosmology and starlight, a record of hierarchical growth, mergers, stripping, and cluster assembly. And that's the key tension line. If the outskirts are dominated by accreted stars, then the boundary between galaxy halo and intracluster light is not just a measurement nuisance. It's the physical story of how clusters build their centers. So here's the next question, and it tightens the screw. If the stars in the outer regions came from many sources, then their motions should not behave like a normal isolated galaxy. So what happens when you stop looking at the light and start clocking the stars, how they move, to see what gravity is really in control? What if the light is lying to you? And the only way to catch the lie is to measure motion. C1101 looks huge in images, but images only tell you where the light is. They do not tell you what gravity is controlling that light. Kinematics is the lie detector here. You measure how stars move, and that motion tells you what mass is really in charge. If the outer stars are mainly bound to this galaxy, their motions should match the galaxy's own gravitational pull. If the outer stars are mainly moving in the cluster's gravitational field, then the cluster is in control, and the outer light is not just galaxy halo anymore. So what do astronomers actually measure? The basic observable is velocity dispersion. That is the spread in speeds of stars along your line of sight. How fast they are moving in many random directions. In big ellipticals and brightest cluster galaxies, stars are usually not moving in a clean rotating disk. They are moving in a swarm-like way, random orbits, supported by dispersion rather than rotation. You measure dispersion using spectra. The absorption lines in the galaxy's light get broadened because different stars are moving at different speeds toward you and away from you. The broader the lines, the higher the dispersion. That gives you a number, and you can measure how that number changes with radius. That is the velocity dispersion profile. Now here's the key idea that changes everything. If dispersion stays high at large radii, you're not just feeling this galaxy's gravity, you're feeling the cluster potential. Because a normal galaxy, even a huge one, has a gravitational influence that weakens with distance. In the outskirts, if the galaxy were isolated, you would expect the velocity dispersion to fall as you go outward, because the enclosed mass stops rising fast enough to keep star speeds high. But in a cluster center, the enclosed mass keeps rising because you're inside a much larger dark matter halo. So the dispersion can stay high, or even rise, because the background gravity is enormous. And this is how you detect the transition zone, the region where the galaxy outskirts stop behaving like a galaxy and start behaving like the cluster core. Now here's the complication. You can't easily measure stellar motions where the light is extremely faint. The center is bright. The spectra are easy. The outskirts are brutal. The signal is weak. And you need deep observations. So astronomers often use tracers. Globular clusters are a big one. Dense star clusters that can be seen farther out than the diffuse starlight. Planetary nebulae are another. They are bright in specific emission lines and can be used like motion markers in faint regions. Sometimes people also use integrated light spectroscopy with very long exposures to push dispersion measurements outward. The goal is the same: map how motion changes with radius, then infer which gravitational field is dominating. And when you do this, you get a physical answer, not a definition based on brightness thresholds. Now let's hit rotation, because rotation is the other part people misunderstand. In spiral galaxies, rotation is the main support. Stars move in an organized disk. In giant ellipticals and central cluster galaxies, dispersion is usually the main support. That means the galaxy is held up by random motions, not by spinning like a wheel. But rotation is still important, because any rotation signal in a giant system is a clue about history. If you detect rotation in the inner region, that can point to certain merger geometries, like mergers that brought in angular momentum in a consistent direction. If rotation is weak or complex, that can point to many mergers coming from many directions, which tends to cancel out ordered spin. So when you compare rotation versus dispersion, you're reading formation history in the language of motion. High dispersion and low rotation, that usually means repeated mergers and a pressure-supported structure. A stronger rotation component, that can mean the system formed with more coherent angular momentum at some stage, or that a particular merger left a lasting imprint. Now focus on what makes this galaxy special in this exact case. It sits at the center of Abell 2029, so the background gravity is not a small correction. It is the main stage. The cluster dark matter halo dominates the mass budget on large scales. The hot gas traces the potential. The galaxy is embedded inside all of that. So when you take kinematic measurements, you're not just weighing the galaxy, you're probing the combined galaxy plus cluster mass distribution. And you are looking for where one stops being the main influence and the other takes over. This is why kinematics can separate galaxy halo from intracluster light in a way photometry cannot. Photometrically, the outer envelope can look smooth, continuous, like one object. But kinematically, intracluster stars should behave more like the cluster population. Their velocities should reflect the cluster's deeper potential, often higher dispersions, and sometimes different anisotropy, meaning different mixes of radial versus tangential orbits. If the outer light is mostly galaxy-bound, you should see a motion pattern that is more consistent with the galaxy mass profile. If it is mostly cluster-bound, the dispersion profile can flatten at a high value or trend toward the cluster's characteristic velocities. And here is the escalating implication. Once the motions are dominated by the cluster, the phrase "this is one galaxy" becomes an approximation, not a fact. Because what do you mean by one galaxy then? Do you mean one continuous light distribution, even if the stars are orbiting the cluster? Do you mean a region where stars share a common potential dominated by the galaxy itself? Do you mean the inner component only, where the galaxy is clearly in control? Kinematics forces you to pick a physical definition, because motion tells you who owns the orbit. And this is where the stakes get sharper than before. If a big part of the outer light is moving in the cluster potential, then the extreme size claims are not just about a giant galaxy, they're about how much starlight is sitting in the cluster core as a shared component. That changes the interpretation of largest galaxy instantly. It also changes how you estimate total mass, how you connect light to dark matter, and how you model the assembly history of the cluster center. So kinematics is not a side measurement. It is the switch that flips the whole story from looks huge to is physically this huge and bound as one system, or is huge because it blends into the cluster. Now here's the next tension step, and it pushes you straight into the invisible. If the motion tells you the cluster is dominating a large radii, then you need a direct way to map that mass. without trusting light at all. So what happens when you weigh the system using gravity itself, through dark matter mapping and lensing, and you find out the stars are just the bright top layer of something much larger? How do you measure the mass of something when most of it is invisible and doesn't emit light? C1101 can look like the main character, but the real structure controlling everything is the dark matter halo of Abell 2029. If you want to understand the size of this galaxy, and whether its outer light is actually bound to it or mainly controlled by the cluster, you need a mass map, not a light map. A mass map. And the cleanest way to get that, without assuming what the matter is made of, is gravitational lensing. Weak gravitational lensing is the method that lets you do this. The concept is simple. Gravity bends light. A massive object between you and the distant background galaxies slightly distorts the shapes of those background galaxies. Not in a dramatic Einstein ring way most of the time. That would be strong lensing. Weak lensing is subtle. It makes tiny statistical changes in the apparent shapes and orientations of many background galaxies across a wide area of the sky. The power is that lensing does not care what the mass is. It does not care if the mass is stars, gas, or dark matter. It only responds to gravity. So if you build a lensing map for Abell 2029, you get a direct check on the cluster's gravitational field. You get a way to measure where the mass is distributed, how concentrated the core is, and how the total mass grows with radius. Now, why does this matter specifically for this galaxy? Because the outer envelope and the faint outskirts exist inside the cluster's dark matter halo. That sounds obvious, but the consequence is huge. If you don't know the cluster mass profile, you can't interpret outer kinematics correctly, and you can't interpret the boundary between galaxy halo and intracluster light physically. The same starlight at the same radius can be bound mainly to the galaxy or mainly to the cluster, depending on how the mass is distributed. So without the mass map, you're arguing about size, using brightness and assumptions. With the mass map, you can ask the real question: what gravitational field dominates the orbits at each radius? This is also why lensing is the perfect partner for the earlier kinematics discussion. Kinematics tells you how stars and tracers move. Lensing tells you how much mass is actually there to cause that motion. Put them together, and you can test if your model makes sense. If the outer dispersion stays high, lensing can tell you if the cluster mass profile is strong enough to explain it. If lensing shows a certain concentration and mass scale, you can predict what motions you should see. That is how you move from maybe to measured. Now here's the observational reality. Weak lensing is hard. The signals are tiny. Individual background galaxies have their own shapes, so you can't look at one and say that's lensing. You need large numbers. You need deep imaging to detect many faint background galaxies. You need a wide field because the lensing pattern extends across the cluster region and beyond. You also need careful correction for the telescope's point spread function, because the optics can distort shapes too, and that can mimic lensing if you're sloppy. So lensing reconstructions are statistical. You measure the average alignment patterns of the shear across the field. Then you invert that shear field to estimate the projected mass distribution. It's not magic, it's careful measurement and careful modelling. And when it works, it gives you something you can't get any other way. A mass map that doesn't rely on assuming the gas is perfectly calm or the stars trace mass cleanly. Now hit the shatter moment, because this is where the story stops being about a huge galaxy and becomes about the structure that makes it possible. The biggest galaxies aren't just big piles of stars, they are the bright top layer sitting on top of an enormous dark matter structure. The starlight is the part your eyes and telescopes catch easily. The dark matter is the scaffold that actually sets the gravitational landscape, this galaxy's growth, its outer envelope, the fate of stripped stars, and the transition to intracluster light, all happen inside that invisible framework. So if you only focused on the starlight, you miss the main controlling variable. Now the payoff, because this is where you stop relying on one method and start triangulating. You combine weak lensing, stellar kinematics, and X-ray gas measurements. Lensing gives you mass distribution without caring what it's made of. Stellar kinematics tells you how the luminous traces respond to the gravitational field and where the motions start to look like cluster-dominated behavior. X-ray observations of the intracluster medium give you density and temperature profiles, which can also be used to estimate the mass profile if the gas is close to equilibrium. And they tell you about physical processes like cooling, heating, and disturbances. When these three agree, you get a strong cross-checked picture. When they disagree, that disagreement is not a failure, it's a clue. It can mean the gas has turbulence or bulk motions. It can mean the system isn't perfectly relaxed. It can mean your assumptions about equilibrium are wrong. Either way, you learn more, and for understanding this galaxy, that triangulation is the difference between it looks huge and we know what gravitational field dominates at each radius, and we can say what is bound to what. Now here's the tension step that pushes you forward. Course, lensing weighs the mass, but it doesn't tell you how the cluster got that way or what the gas is doing right now. So what happens when you look at the cluster in X-rays and you find temperature changes, chemical patterns, and large-scale structure in the gas that acts like a historical record of past disturbances? How can a cluster look calm and still have hot gas doing something violent on scales bigger than most galaxy groups? IC1101 sits at the centre of Abell 2029, and if you only look in optical light, you can miss the biggest clue about how this galaxy got so massive. The clue is not more stars, it's the hot gas around it. The space between galaxies in a rich cluster is filled with plasma so hot it shines in X-rays, and that gas reacts directly to gravity, mergers, and feedback. So if you want to know what fed this galaxy over time, you read the cluster's X-ray anatomy like hard evidence, not vibes. Start with the temperature profile because it tells you the core is physically different from the outskirts. Chandra measurements show the intracluster medium dropping from about 9 keV farther out to about 3 keV very close to the centre. In plain language, the gas is much hotter at large radius and significantly cooler in the core region. That pattern matters because it means the core gas is denser and can cool faster, and it also means the cluster is not one uniform atmosphere. The centre is a special zone where cooling, heating, and structure fight each other over billions of years. Now slow down for 1 second, because KeV can sound like nonsense. In X-ray astronomy, KeV is just a standard way to express temperatures of extremely hot gas. We're talking tens of millions of degrees. So a drop from 9 to 3 is a big change, not a small fluctuation. It tells you the core gas is cooler, and that's connected to the idea of a cool core cluster. Cool cores are important because they are where you expect strong cooling, but also where you often see feedback that prevents runaway cooling, like energy injection from the central active black hole. And Abell 2029 has been studied exactly because it looks like a strong cool core system, yet it doesn't behave like the old simple cooling flow story would predict. So what does this do to the galaxy environment? A cooler dense core means higher gas density in the centre, and that affects pressure, stripping, and how satellites lose their own gas. It also means the cluster core can keep supplying conditions that make the centre a special place for long-term growth, not by forming lots of new stars necessarily, but by controlling how galaxies get processed as they pass through. When galaxies orbit through this core, their outer material is easier to strip, and that stripped material becomes part of the diffuse light around the center. The X-ray gas is basically telling you the cluster core is a controlled high-pressure environment, and it keeps influencing what happens to galaxies that enter it. Now here's the detail that should snap your idea of relaxed cluster in half. Deep Chandra observations show a huge sloshing spiral in the hot gas, extending to nearly 600 kiloparsecs from the core. Nearly 600. That is not a tiny disturbance. That is a massive structure in the intracluster medium, and it's direct evidence the cluster was disturbed, even if the overall shape looks smooth and relaxed at first glance. So what is sloshing in plain language? It's when the dense, cool core gas gets displaced from the exact center, usually by a gravitational perturbation from a merger, often a smaller subcluster passing by off-center. The core gas doesn't just move once and stop, it oscillates in the cluster potential, and that motion sets up spiral-like patterns and sharp edges called cold fronts, where cooler, denser gas sits next to hotter, lower-density gas. Over time, you can literally trace the history of that disturbance because the gas keeps a memory of the motion as a structured pattern, not random noise. This matters for the growth story because sloshing is not just gas doing something pretty. It is a merger signature. It says, the cluster's been poked and stirred. Maybe the cluster looks relaxed in the big picture, but sloshing means it has experienced interactions that displace the core, and those interactions are exactly the kind of events that drive stripping, orbit changes, and long-term mass delivery toward the center. Even a minor merger can set off sloshing that lasts a long time. So the gas is telling you, the environment that built this galaxy was not perfectly quiet. It had repeated disturbances that keep rearranging the core conditions. And notice the escalation here. A sloshing spiral out to nearly 600 kiloparsecs is huge enough that it connects core physics to the wider cluster structure. It means the disturbance affected a big fraction of the central region where galaxies orbit. That changes where stripping is strongest, where pressure is highest, and where material ends up. It also means the idea relaxed equals simple is not safe. The cluster can be relaxed in the sense of having a strong cool core and a smooth overall profile, while still containing large-scale internal structure that came from past interactions. Now add the chemical evidence, because X-rays don't just tell you temperature, they tell you composition. The intracluster gas contains heavy elements made by supernovae, especially iron, and you can measure how the abundance changes with radius. Abell 2029 shows a steep iron abundance gradient, with very high iron abundance in the core and lower abundance farther out. In normal language, the core gas is more enriched, meaning it has been polluted by many supernova explosions over time, especially type E supernovae associated with older stellar populations, and the enrichment is not uniform, it's concentrated toward the center. Why should you care about that? Because it links the central galaxy to the cluster medium over long times. Metals in the gas don't appear by magic. They come from stars. They get injected by supernovae and outflows. If the core gas is metal-rich, that tells you the center has been enriching the surrounding medium for a long time, and it also tells you the gas has not been completely mixed away. The gradient surviving means the cluster core has structure and history, not just a stirred pot. And when you see metals concentrated in the center, that's evidence that the central region has been active, forming stars earlier, then enriching the gas, then having that gas move around through sloshing and feedback. Now connect all of this back to the main point and keep it simple. This galaxy is not just an optical object with a big halo. Its growth is tied to a cluster core that has a cool temperature structure, chemical gradients, and large-scale gas motion signatures. The X-ray data is telling you how the environment behaves, how it gets disturbed, how it moves, and how it stores a record of past interactions. If you want to understand why the central galaxy got so massive, you can't ignore the X-ray story because the gas is tracing the same gravitational events that drive mergers and stripping, and it is literally showing you the mechanisms that can keep feeding the center over time. And now the tension goes up again, because once you admit the gas is moving and sloshing on huge scales, you have to face the next problem. What if the cluster is not as equilibrium as we assume, and those hidden gas motions are biasing the mass estimates we use to interpret everything, including what is bound to the galaxy and what belongs to the cluster? What if the cluster mass you've been using this whole time is slightly wrong because the gas is moving and you didn't account for it? IC1101 is the famous giant in this story, but the next jump in precision is not about taking prettier images of this galaxy. It's about measuring the motion of the hot gas in Abell 2029 directly, because gas motion can quietly bias how we weigh clusters in the first place. High-resolution X-ray spectroscopy is the upgrade. It doesn't just tell you temperature and composition. It can measure Doppler shifts and line broadening in the X-ray emission lines, which means you can measure bulk flows and turbulence in the intracluster medium. Here's the basic problem. A lot of cluster mass estimates assume the gas is close to equilibrium. The logic is, hot gas pressure balances gravity, so if you map gas density and temperature, you can infer the mass needed to hold it in place. That method can be very powerful, but it has a weak point. If the gas has extra support from motion, like turbulence or bulk flows, then part of the pressure is non-thermal. If you ignore that non-thermal support, you can underestimate the true cluster mass. And if you underestimate the cluster mass, you misread the gravitational field that controls the outer regions around the central galaxy. So what does XRISM change? XRISM carries a microcalorimeter spectrometer called Resolve, built to deliver very high spectral resolution for extended X-ray sources. With this level of resolution, you can directly measure small shifts in the energies of X-ray lines. That's the Doppler effect in the hot gas, and you can measure how much the lines are broadened, which tells you turbulence and unresolved motions. In normal language, you can finally clock how the cluster atmosphere is moving, not just how hot it is. And this matters because relaxed clusters are exactly where hidden motion is most dangerous. Abell 2029 is often treated as a prototypical massive cool core cluster with an apparently relaxed X-ray morphology, the kind of system people like to use as a clean laboratory. That's precisely why it's a prime target for gas motion measurements. If you find significant non-thermal pressure even here, then the idea relaxed equals equilibrium becomes much less safe. XRISM collaboration work frames the key question in a blunt way. Do calm-looking clusters truly sit in dynamical equilibrium, or do they hide bulk motions and turbulence that change the accounting? Now connect this to what you already know about this cluster. Chandra shows strong structure in the core, including sloshing features on enormous scales, which is already a hint that internal motion exists even when the cluster looks broadly smooth. A deep 2025 Chandra analysis describes a very extended sloshing spiral reaching nearly 600 kiloparsecs, meaning the core has been disturbed and is still carrying a memory of that disturbance. If the gas is sloshing on that scale, it would be strange to assume the pressure is purely thermal everywhere. So the XRISM-era measurement is basically this. don't guess the motion, measure it. When XRISM measures the velocity field and turbulence across multiple pointings, you can estimate how much non-thermal pressure exists as a function of radius, and that directly feeds into hydrostatic mass bias, meaning how wrong your equilibrium-based mass estimate might be. XRISM collaboration work on Abell 2029 specifically focuses on constraining bulk and turbulent velocity components and translating that into non-thermal pressure support and a mass bias, because that's the lever arm that affects everything else you infer. Now here's the loop back to this galaxy, and it's not optional. If the cluster mass profile shifts after you include gas motions, then your interpretation of what's bound to the galaxy versus what's bound to the cluster shifts too. A stronger cluster potential at a given radius means the outer stars and tracers are more likely to be dominated by the cluster field, which pushes more of the faint outer light into the intracluster category physically. A weaker cluster potential would pull the other way, making it easier for the galaxy's own halo to remain the main binding influence farther out. Either way, the boundary debate is not solved by arguing about brightness thresholds, it's solved by getting the gravitational field right. This is the shatters what we thought beat, and it's very concrete. Even clusters we call calm can have internal motion that changes the mass estimate, and once the mass estimate changes, the whole story about size and membership changes. You thought you were measuring a galaxy plus a halo. Then you realize you are also measuring how the cluster atmosphere moves, because that motion affects the cluster mass you used in the background. The universe is not giving you simple systems to measure. It gives you systems that look simple until you measure a new variable. And the forward-looking angle is the real payoff. XRISM class measurements are how you turn a big galaxy story into precision cosmology. When you can combine X-ray gas velocities and turbulence with X-ray temperature and density, with weak lensing mass maps, and with stellar and tracer kinematics, you can cross-check the mass profile from multiple directions. If they converge, you gain confidence in the cluster mass and its assembly state. If they don't, you learn exactly which assumption broke: equilibrium, projection, substructure, or non-thermal pressure. This is how you move from arguing about definitions to measuring physical membership in a cluster core. Now here's the next question, and it raises the tension again. If you can measure gas motion and correct the mass, and you already have signs of sloshing and past disturbances, then the next step is brutal. How does a central galaxy actually become this extreme over billions of years? And what sequence of events builds a structure that big without making it look obviously chaotic today? How do you build something this huge without creating most of its stars? IC1101 forces you to face the real growth chain for brightest cluster galaxies. And it's not the same chain that built the Milky Way. This galaxy mainly grows by taking stars that already exist, not by making huge amounts of new stars. The central location inside a massive cluster changes everything, because it makes repeated mergers more likely, and it makes tidal stripping efficient over very long time periods. Here's the main channel in plain terms. Galaxies fall into the cluster. They orbit through the core. Over time, their orbits can decay, especially for more massive galaxies, because they lose orbital energy through dynamical friction. As they sink inward, they experience stronger tidal forces from the cluster and from the central galaxy. Their outer stars get stripped first. Those stars spread out into a diffuse component, and the remaining core can eventually merge into the central galaxy. Repeat that again and again over billions of years, and you build a central system that keeps getting bigger, even if it isn't forming many new stars. This is the part people miss. Growth is not one event. It's a long sequence. Some mergers are major, 2 large galaxies combining. Many are minor, smaller galaxies being absorbed. Stripping happens continuously in the background, not only during direct collisions. Each pass through the core can remove more material. The result is not just more mass. The result is a specific structure, a dense inner component, plus a very extended outer envelope, plus a surrounding population of stars that are not bound to any one galaxy. And when you look at what we actually observe in this galaxy, lines up with that chain in a very direct way. Depletes core? Check. A large depleted core is what you expect after multiple major mergers, because each major merger likely brings in a supermassive black hole. And black hole binaries can eject stars from the center over time. That's a central signature of repeated violent growth. An extended envelope? Check. A huge faint outer light component is what you expect if the system has been accreting stars from many sources, and if stripped stars from incoming galaxies keep getting added to the outskirts. A normal isolated elliptical can be big, but the kind of very extended diffuse envelope seen in many central cluster galaxies is exactly what long-term merging plus stripping produces. A surrounding intracluster-like component? Check. If you strip stars from many galaxies in a dense cluster core, not all of those stars end up neatly bound to the central galaxy. Some end up orbiting mainly in the cluster potential. That creates intracluster light, a real population of stars spread through the core, and photometrically, that light can blend into the outer envelope, which is why where does the galaxy end becomes a real physical problem. Now here's why simple diameter comparisons mislead. And this matters because it's how people get the wrong intuition fast. The Milky Way grows in a mixed way. It forms stars from gas over time. It merges sometimes. But a lot of its mass and structure comes from long-term star formation in a disk. That means its size and shape are strongly tied to gas physics. Ongoing star formation and internal evolution. This galaxy grows differently. In a dense cluster core, gas gets stripped and heated. Star formation is often suppressed. So growth becomes dominated by accretion of whole galaxies and redistribution of stars. You're not mostly building new stars. You're mostly moving stars around, adding already formed stars from other systems, and spreading them into a larger structure through merging and stripping. That's why comparing diameters like it's a simple competition is the wrong frame. A galaxy that grows by star formation can have a large disk, but it's limited by how gas settles and how feedback regulates star birth. A brightest cluster galaxy can get enormous because it is collecting and rearranging existing stellar mass from many other galaxies, and the cluster environment keeps delivering material toward the center over long times. And we have an empirical constraint that makes this growth chain even harder to ignore. The cluster's X-ray structure shows evidence of disturbances like sloshing. That means the cluster has not been perfectly quiet. It has been perturbed by interactions over time. Those interactions don't just move gas, they also change orbits. They help drive stripping, they can bring in substructure, and they can keep feeding the central region with new galaxies and new material to process. So the X-ray evidence supports the idea that the cluster had a merger history capable of sustaining long-term central growth, even if the cluster looks broadly smooth today. Now push the stakes higher, because this is the point where galaxy growth stops being one story. This galaxy makes you confront that growth is not a single process with one rule. It's a menu. In low-density environments, you get one set of dominant processes: star formation, disk growth, moderate mergers. In rich cluster centers, you get a different set dominating repeated mergers, strong tidal stripping, and the creation of a diffuse stellar component that can be partly galaxy halo and partly intracluster light. And once you accept that, the largest galaxy question becomes sharper, not softer. Because you're not just asking how wide is it, you're asking what physical component am I measuring? The bound inner galaxy, the bound halo, the extended envelope built from many mergers, or the cluster's shared starlight mixed into the same smooth profile. So here's the next tension question, and it should feel like the story is tightening around one unavoidable conclusion. If largest depends on definitions and on separating halo from intracluster light, what does this galaxy force you to admit about the word galaxy itself when you reach the biggest scales? So here's the final problem. What does largest galaxy even mean when the boundary is not a boundary? 1101 really is one of the largest and most luminous galaxies known by the common optical and infrared size metrics. That's the honest claim, and it's not just internet hype. Even when you use conservative isophotal thresholds, you still end up with an enormous diameter compared to normal giant ellipticals. Even when you avoid the most extreme halo claims, it still sits in the top tier of known galaxies by size and luminosity. But the second half of the honest claim matters just as much. Largest depends on definition, and it depends on whether you can separate galaxy halo from intracluster light in a physically meaningful way. And this is the part people try to brush off as technical, but you can't. This is not pedantry. The boundary problem is the science. Because the whole question is literally about how stars get stripped, where those stars orbit, and what structures actually exist in cluster centers. If you say, count everything you can detect as part of the galaxy, you might be counting stars that are no longer bound to the galaxy at all. If you say only count what is definitely bound, you might cut off a real bound halo just because it's faint and hard to measure. Every shortcut is choosing a physical story, whether you admit it or not. So when people argue about whether this galaxy is 400,000 light-years wide or 550,000 light-years wide or more, that argument is not about ego. It's about membership. It's about whether the outer starlight is controlled mainly by the galaxy's own gravity or mainly by the cluster's gravity. And once you ask it that way, you realize largest galaxy is not a clean trophy title. It's a question about how matter is organized in the densest environments in the universe. Now here's the clean way forward, the data-driven way, the way you stop guessing. You combine deep surface brightness imaging with kinematic, with lensing mass maps, with X-ray gas dynamics. Deep imaging tells you the shape of the light profile down to very faint levels, but it can't prove what is bound to what. Kinematics tells you how stars and tracers move, and motion is the physical clue about which gravitational field dominates at different radii. Weak lensing gives you a mass map of the cluster that doesn't care about what the mass is made of, so it checks the gravitational potential directly. X-ray data tells you the gas temperature, density, metals, and with modern high-resolution spectroscopy, it can tell you gas motions too. Which matters because gas motion affects mass estimates and tells you how disturbed the cluster really is. When you put these together, you can define membership based on physics, not on a brightness cutoff and not on vibes. You can look for the radius where kinematics transitions from galaxy-like to cluster-like. You can compare that to where the mass profile from lensing says the cluster dominates. You can check that against X-ray structure and gas motion that shows whether the cluster is close to equilibrium. You can test whether the diffuse light follows the cluster mass distribution like intracluster light should, or follows a galaxy halo profile more tightly. That is what solving the boundary actually means, not drawing a prettier line, but identifying a physical transition. And this is the shatter closing beat, and it's not a slogan, it's what the data forces on you at the largest scales. Galaxy stops being a single object and starts being a gradient, a transition region, a zone where the inner stars are closely bound to the galaxy, but the outer stars gradually become more mixed, more cluster-dominated, more like intracluster light. In a cluster center, there isn't a clean edge in the way your brain wants. There is a smooth fade in brightness, and often a smooth transition in what gravity dominates. The biggest central galaxies are not isolated islands. They are the brightest concentration inside a much larger gravitational ecosystem. So here's the final hook, and it's the real ending because it's the real lesson. The C1101 isn't just huge, it's the universe showing you that categories are human-made and gravity doesn't care. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.